Hello, everybody. Welcome to Medication Math for Advanced EMTs. As always, I encourage you to take good notes. When you're done taking the notes after we get done talking today, take yourself a break. Go get something to drink. Excuse me. Rest, relax for a little bit, then go back. Clean up your notes into a smooth flow. Your notes should bring back memories of what was discussed so they can be comprehensive. They should be all-inclusive, and they should be able to be something you could come back later and jump right back into it and remember what you're doing and refer to quickly. A few weeks from now, you may want to go back and even redo them again. This should be part of the Renote project. Whenever you come in before your final exam, you'll have to show all your notes in a clean format that you've taken throughout the program here. So be sure that this is one of them. You're going to want to title this Medication Math for Advanced EMTs. Medication Math for Advanced EMTs. We'll be working out some equations, and I will explain the equations to you. And as you hear the equation, write it down in the best way that you can. And we will go through it several times. And then there will also be emailed to you a list of questions for you to convert the metric system, as well as drip calculations and drug calculations. Some of the medications we will talk about will be paramedic medications, and that's okay. In many instances, you'll be assisting the paramedic and having a good skill set with base knowledge of what the paramedics are doing, or even in the hospital, what the nurses and doctors are doing. Only makes you stronger and has better outcomes for the patient. So if you see a drug that you recognize from either the hospital or the ambulance, but not on our drug formulary yet, that's okay. Just consider it a bonus, and we'll move forward with that. Getting started, trust me, you need to know this stuff. There's no substitute. There's no talking a big game and then not being prepared to start the race. You've got to learn it. And if you want to follow along in your book, then the book I'm referring to is Advanced Emergency, 2nd edition, Care and Transport of the Sick and Injured, the 40th University Orange Book Series. The editor is Andrew N. Pollock, MD, FAAOS. The section that we'll be discussing and referring to today starts on page 278 and goes through page 282. Our information will not be directly from the book in this lecture, but you should read that section over and over because it has very nice examples of the conversions in the metric system. And in the U.S., we don't do a lot of the metric system unless you are in medicine. And guess what? You're in medicine. So let's get started. In the EMS setting, we worry about 3 metric units of measurement. The first being the gram, which is a designation of weight, and it is the acronym for gram would be a lowercase g. Number 2 would be meters, which is a designation for distance, and the abbreviation would be a lowercase m. And then 3 is liters, and you can write that as a capital L or lowercase l, and it is a designation for volume. When you put these together, you're going to come up with some larger units. Number 1, the kilogram is 1,000. The centi or centigram is 1/100th, which is written 0.01. The milli or the milligram is what you're probably more comfortable with hearing, is 1/1000th is 0.001, and the micro is 1/millionth or 0.000001. So the kilogram would be 1,000, the centi would be 0.01, the milli would be 0.001, and the micro would be 0.000001. So if we combine those together, if we make a kilogram, it'd be abbreviated as kg. The gram would be g. The milligram would be mg, and these are all lowercase. The microgram would be mcg. The centimeter would be cm. The liter would be a capital L. The milliliter would be ml. And if we put that all together, we can actually start working some problems and bringing things together to form what we will be doing in our medication math. If you're going from the smaller unit to the larger unit, you simply move the decimal to the left. So, for example, milligrams to grams, you'd move the decimal 3 points to the left. So let's do an example. If you have 740 grams and you move the decimal spot to the left 3 places, you have 0.740 grams. If you have 2 milligrams, you move the decimal spot 3 spaces to the left, so you're going to have to add some zeros. 2 milligrams transitions into 0.002 grams. 100 milligrams, you're going to move the decimal spot to the left 3 spots, and you're going to have 0.1 grams. So going from grams to kilograms, you move the decimal spot 3 to the left again. So if we have 4,000 grams, that would be 4 kilograms. So you'd have 4,000, which is 4,000. You move the decimal spot to the left 3, and now you have 4 kilograms. 750 grams, we move the decimal spot to the left 3 spaces, and we would have 0.75 grams. Another one, if we have 93,500 grams, that would be equal to, after moving the decimal spot 3 spaces to the left, 93.5 kilograms. So let's go micrograms to milligrams. We're going to move the decimal spot 3 spaces to the left. Are you seeing a trend here when we're going down? So if we have 250 micrograms equals 0.25 milligrams, we simply move the decimal spot to the left 3 times. 500 micrograms, move the decimal spot to the left. I'll give you a few seconds. 0.5 milligrams, or 0.5 mg. 1,000 micrograms. If you move the decimal spot to the left, you should have 1 milligram. Now, if you're going to go from larger unit to smaller unit, then the decimal point to the right is the direction that you want to make it move. So let's go grams to milligrams. So this time we're going to be moving to the right 3 spots. If we have 50 grams and we're going to go to milligrams, we're going to have to actually add zeros to move it 3 spaces. So we're going to go 50 grams equals 50,000 milligrams. 7,500 grams would be 7,500,000 milligrams. Did you get that right? One number there? There we go. 3 grams, move the decimal spot to the right, is 3,000 milligrams. So let's try kilograms to grams. Again, we're going to move the decimal point 3 spots to the right. So if you have 35 kilograms, we add 3 zeros because we got to be able to move it to the right 3 spaces. We end up with 35,000 grams. Let's try 250 kilograms. Again, got to add some zeros. So we're going to move the decimal spot to the right 3 places. So you should be writing 250,000 kg, or 250,000 kilograms. One last one. 7 kilograms equals, move the decimal spot to the right 3, 7,000 kilograms. All right, so 1 kilogram goes into 1,000 grams, goes into 1 million milligrams, goes into 1 billion micrograms. So now we're done converting those. Let's convert pounds to kilograms, which we'll be doing a lot of in your career. As an AEMT or advanced EMT, you'll be required to quickly convert patients' weight from pounds to kilograms. And there's a couple tricks of the trade, as well as just knowing the basic math. As you're aware by now, this is done for any medication that's weight-based. When the pressure's on, you need to be able to do this fast, and easy to remember conversions are the best way to go. So let's jump in with a patient. You say you have a 200-pound patient, and you need to convert their weight to kilograms so you can administer a medication bolus of 100 or 1.5 milligrams per kilogram. If you've been in the back of the truck with one of the medics, and the medication lidocaine is 1.5 milligrams per kilogram, so let's just use that as our medication. To convert this patient's weight, you can do a couple things. You can take the 200 pounds and divide it by 2.2, and that's going to be your milligram per kilogram rating. Or you can do what we do in the back of the truck with some quick math. The 200-pound patient, you cut the patient's weight in half. Let's say the patient's 300 pounds. 300-pound patient, cut their weight in half, and you end with 150. Now you take that 150 and you take 10% of that number and subtract it from itself. So we get 10% of 150 is 15. So 150 minus 15 is 135 kilograms. Let's try that again. Let's say you have a 40-pound pediatric patient, and you need to convert their weight to kilograms so you can administer a medication of 2 milligrams per kilogram. Cut the patient's weight in half, so 40 divided by 2 would equal 20. You take 10% away from the 20, which would be 10% minus 2, and you end up with 18 kilograms. So let me run by that one more time. You have a 40-pound patient. You're going to divide that patient's weight in half, so that gives you 20. You're going to subtract 10% of 20 from itself, so 10% of 20 is 2. So 20 minus 2 would be 18, and you have 18 kilograms. So when you would be giving the patient medication, you would be giving it so much milligrams per kilogram, and if the medication was 2 milligrams per kilogram, you would take the 2 milligrams times the 18 kilograms, and you would come up with 36 milligrams as you're going to give the patient. All right, converting kilograms to pounds is just working in the other direction. Sometimes we got to do this. You would multiply the patient's weight times 2.2, and you would get the right amount of weight. Or you could do what we've done in the past with doubling the weight and then adding 10%, and to bring it right back into you. We rarely do this. There's some kind of things that are given that are specific, but in the back of the truck, for the most part, you won't be going the other way. You'll always be going pounds to kilograms virtually all of the time. So, some of the glossary of terms that you really got to know, and I hope that you put this in your notes very, very well. In fact, if you'll make a section and just call it glossary of terms, some will be self-explanatory, but we will define them so they won't be confusing. The first term is desired dose. So write desired dose, colon, and let's give a definition of desired dose. Desired dose is the dose we want to administer to the patient. Pretty self-explanatory. Next term that we're going to use is total drug amount. So that's total drug amount and the total amount of the drug within its container. So if you're looking at a container, this is the total amount of drug within that container specific to that drug. Don't get confused if there's different total amounts of drugs in the same size containers. It's all about concentration when we're dealing with medications. All right, next term, total drug volume. Total drug volume. That is the amount of fluid within the drug container. And I've had a lot of students that have been confused when they see one medication that has 10 mils of fluid in it, and the concentration of that 10 mils is 100 milligrams. And they've got another medication that's got 10 mils of fluid in it, or a volume of 10 milliliters. And the concentration of that drug is, say, 5 milligrams. It's all about concentration. And a good way to understand concentration is if you took one glass of water and you put a half a cup of sugar in it and mixed it all up until it dissolved, and you took a drink of it, it would be super, super sweet. Super, super sweet. But if you took that same glass of water and you took a pinch of sugar and threw it in that water and mixed it all up till it's dissolved, you probably wouldn't even be able to taste it. Now, it's the same volume of water, but the concentration of sugar is really strong in one and really weak in the other, and it's the same with the medications. They take the volume and they mix the amount of drug in it to make the concentration desired so they can have the right potency for the patient. And I hope that makes sense with that analogy. All right, let's do medicine concentrations. Fortunately for EMS, most of our medication concentrations are expressed as a unit of volume per weight. Usually you'll see this expressed on a medication as grams per mil or milligrams per mil or micrograms per mil. And when I say that, let's say milligrams per mil, you'll see mg/ml, milligrams per mil. You can find this number on the medication box or the vial. So let's do some work with that. Let's set up some calculations. The most typical calculations in the field are milligrams per mil. So your concentration is milligrams per mil, and the way you figure that is the total drug divided by the total volume. Let me say that again. Concentrations in milligrams per mil is the total drug divided by the total volume. So if you want to take a note, you would write concentration, and then within the brackets there, you'd put milligrams per mil, or mg/ml, equal sign, and then the word total drug / total volume. Concentration is milligrams per mil, is total drug divided by total volume. So let's do some drug problems. Say we're going to give the drug good stuff, and we're going to fill in the numbers and see how good stuff works out for us. So the good stuff concentration is 40 milligrams in 10 mils. So if you divide 10 mils into 40 milligrams, so you would be dividing up, so it'd be 40 mg over 10 ml, and you divide up, so that would equal 4 milligrams for every 1 mil. So 4 milligrams per mil. So your equation would look like 40 mg 10 ml equals 4 mg /ml. So for every mil, there's 4 milligrams. Let me do that one more time. Good stuff concentration is 40 milligrams in 10 mils. So to set your equation up, you would do 40 milligrams over 10 mils. You do the math, and it equals 4 milligrams per mil. Some concentrations are expressed as percentages, like dextrose 50 or lidocaine 2%. You've seen them in the back of the ambulances, I'm sure, with your medics or even in the hospital. There's a very simple way to solve this, so we don't try to make it too complicated. So let's look at the lidocaine 2% first. Take the percentage number, 2%, and make it into grams. So 2% equals 2 grams. Now let's all remember that there are 1,000 milligrams in a single gram. So if we're going to make 2 grams, we're actually talking about 2,000 milligrams. So you can write it, the 2 grams, as a 2,000 milligrams. So if this is confusing, we'll write it in your notes. We'll make it a little more simple. So take the number of grams and place it over 100 mils. So you get 2 grams divided by 100 mils equals 2,000 milligrams divided by 100 mils equals 20 milligrams per mil. This is the concentration seen in the pre-hospital lidocaine vials that you have in the back of the ambulance. So it's very, you're going to see this a lot. So let's try the dextrose 50. All right. Take the percentage of dextrose 50, which is 50%, and make it grams. So 50% equals 50 grams. Take the number of grams and place it over 100. So you get 50 G, or 50 grams, divided by 100 mils equals 50,000 milligrams divided by 100 mils equals 500 milligrams per mil, or 0.5 milligrams per mil. All right, let me read that again. 50 grams divided by 100 mils equals 50,000 milligrams divided by 100 mils equals 500 milligrams over 1 mil equals 0.5 grams per mil. This is the concentration seen on the D50 boxes that we carry on the trucks. So let's move off into bolus medications. Quite often, you'll hear the medic say we're going to give the patient a fluid challenge or a bolus. As an advanced EMT, you will be doing the same thing. When you bolus somebody, you're giving a medication of a specific amount all at once. This can be done with a different drip, where a certain amount of drug is desired slowly over a period of time. AEMTs usually administer medication by bolus instead of drip. Every medication has a solute and a solution leading to a concentration. It is up to you as the AEMT to determine how much you need to deliver and the correct amount of the medication to that patient. Depending on the information you have, you can use one of 2 equations to calculate how many mils of a drug you will need to administer. So let's do some of that math right now. If you want to put this under your section of terms or formulas, you can put X, which is the mils to be given, equals total volume times desired dose divided by total amount of drug. So let me read that to you again so you can write yourself a formula. X equals total volume times desired dose divided by total amount of drug. So if you wrote that out, you'd have like a fraction, and you have X equals, and then at the top, total volume times desired dose, and beneath that, under the line, you'd have total amount of drug. X equals total volume times desired dose divided by total amount of drug. All right, so now if we do the math, then you'd go to the next step, which would be X equals desired dose divided by concentration. All right, so let's try some bolus calculations and see where we're getting. Our medication is called funky drug, and you need to administer 15 milligrams of funky drug to a patient. The funky drug is supplied in a vial that contains 25 milligrams in 5 mils. Funky drug is supplied in a vial that contains 25 milligrams in 5 mils. How many mils will you need to draw up? All right, so X equals volume, which is what we're going to give to the patient. The total amount of the drug is 25 milligrams. Remember I said the vial contains 25 milligrams in 5 mils? So the total amount of the drug is 25 milligrams. So you can write for your notes, total amount of drug, 25 milligrams. Underneath that total volume, how much volume do we have of funky drug in the vial? Well, there's 5 mils. So the total volume would equal 5 mils. Now, the desired dose is what was ordered. The original order said you did need to administer 15 milligrams of funky drug to a patient. The funky drug is supplied in a vial that contains 25 milligrams and 5 mils. So the desired dose is 15 milligrams. So now you should be able to look that you have all the information set up in front of you. And so let's plug in our formula, which is X, which is what we want to give to the patient, equals total volume times desired dose divided by total amount of the drug. So we just start plugging in numbers based off what we have. So we'll have X equals total volume. Well, if we look back at our notes, total volume is 5 mils times the desired dose. Well, the desired dose was 15 milligrams divided by total amount of the drug. Well, total amount of the drug is 25 milligrams. So you should have X equals 5 mils times 15 milligrams divided by 25 milligrams. So the next step would be to do some math. X equals, after you do your calculation there of 5 times 15, 75 mils over 25. Now cancel out the milligrams. So just draw a line through your milligrams. So you'll have 75 ml divided by 25. Do the math, and X equals 3 mils, and 3 mils is what we need to give to the patient to get the 15 milligram dose that was ordered. Hope that makes some sense. Let me do that one more time. X, plug in the numbers, total volume would be 5 mils times desired dose of 15 milligrams divided by the total amount of the drug. We do our next step in our math process would be X equals 75 mils, that's that 5 mil times 15 milligrams, divided by 25 milligrams, cancel out the milligrams because there's a milligram on the top and a milligram on the bottom, and you're going to end up with X equals 3 mils, and that's what we need to give to get our 15 milligrams. All right, let's do another one. You have a patient in cardiac arrest, and we're going to give him 300 milligrams of the drug wake-up juice. The drug wake-up juice is supplied in a pre-filled syringe that contains 450 milligrams in 3 mils. Write that down. Wake-up juice, 450 milligrams in 3 mils. Now the question is, how many mils will you need to draw up? All right, so let's do our little spreadsheet here. You're going to write out volume, concentration, and desired dose. Volume, concentration, desired dose, one under each other, and we'll put some information with it. So volume, which is what we're going to give to the patient, is X. So X equals volume, which is the mils to be given to the patient. The concentration, as we wrote down before, of wake-up juice is 450 milligrams in 3 mils. So that's 450 milligrams divided by 3 mils. And you come up with, if you do the math, divide 3 up into 450, 150 milligrams per mil. So your concentration is 450 milligrams in 3 mils, written out as 450 mg divided by 3 ml equals, do the math, 150 mg per ml. So you'd write that 150 mg / ml. So our desired dose is 15 milligrams. So let's go ahead and work that through. So X equals the mils to be given equals desired dose divided by concentration. And now we fill in what we know. X, which is mils to be given, equals 300 divided by 150 milligrams per mil. The milligrams cancel out, so do the math. 150 goes into 300. You get X equals 2 mils. All right, very, very good. Again, you're going to go back and clean up your notes, listen to this again and again, and work it different ways and come up with your answer. Let's get into IV drip rate functions. Here's some new terms for you. If you want to go back and find your terms section, I'll give you just a minute. The first term that you should write down is maintenance drip. Maintenance drip. Now, a maintenance drip allows you to maintain the therapeutic levels of a drug after giving a bolus. And we remember a bolus is something that you're going to give all at once. So maintenance drips are usually dripped in at a specific rate, such as 15 mils per hour, instead of a specified dose of 300 milligrams over time. All right, next term, bolus over time. Bolus over time. Some treatments must be administered over a certain length of time because the concentration, if you gave a drug too swiftly, might be actually hazardous to your patient instead of therapeutic. Take, for instance, wake-up juice. Let's say we give wake-up juice for a fast cardiac dysrhythmia with a pulse. So the patient has a pulse, but they're super, super fast. Their heart's beating really, really fast. It's really tacky. And say our protocol states we give 150 milligrams of wake-up juice over 10 minutes. And our concentration wake-up often comes in the 150 milligrams in 3 mils. And how would you suppose to give the 3 mils over 10 minutes? Well, this is what we do. You'd mix a 100 mil bag of normal saline and start an IV drip. Now, the AEMT, this is nothing that we'll be doing, but understanding the math is not outside of our skill set, as we said before, because you might be assisting the medic or in the hospital, and it's always good to have a second set of eyes. So bolus over time is a bolus of a medication or a volume of fluid over a specific amount of time. All right, next term, drip to decrease potential effects. Some of the drugs we give are very potent and can cause adverse reactions and side effects that need to be avoided in certain circumstances. For example, your paramedic is given nitroglycerin to relieve chest pain. That's what we use it for. You know, patients take it at home all the time, but you remember as an EMT, you have a limited amount that you can give, and let's remember the reason why you have a limited amount. Nitro has a side effect that can cause dangerously low blood pressures. So the sublingual dose of nitroglycerin is 0.4 milligrams or 400 micrograms. Look there, we moved the decimal point to the left, right? 3 spaces. And if it's administered all at once, a nitroglycerin drip is started at 10 micrograms, which means we're given 1/40th of the sublingual dose given over a minute. By administering nitroglycerin via drip, you can titrate or make the changes that affect the patient in the right way, the desired effect that you want. You can titrate the drug to relieve the pain and reduce negative effects and not have the trouble with the blood pressure that you would if you just gave them a big old bolus. All right, so in your terms, let's do some IV drip components. Initially, you have your IV bag. An IV bag is a solution to be administered to the patient. The bag can be regular fluid, such as normal saline, or it can be drug mixed with it. Some IV bags in the ambulances come pre-mixed. That's for ease of use in rapid situations. You'll see your medics may have pre-mixed lidocaine or pre-mixed dopamine, while others that they have to mix on their own, maybe something like epinephrine. Your next term is a drip set. An IV drip set is a set that connects the IV to the bag. It's the actual IV catheter attaches. A drip set is categorized by how many drips it takes to administer 1 ml of solution. I'll read that again. A drip set is categorized by how many drips it takes to administer 1 ml of solution. There are 2 types of IV drip sets, macro and micro. That's macro and micro. A macro drip set produces larger drops, requiring 10 to 15 drops per mil. That's depending on who makes them. Micro drip sets produce small drops, requiring 60 drops per mil. I'm sure you've seen it in the back of the ambulance or in the hospital. The micro drip sets got the big chamber on it and the little bitty needle pin looking thing with the little bitty baby drops, and they drop really fast sometimes. That'd be your micro drip sets, and we call them the 60 drop sets. A drop set, we abbreviate the word drop with the acronym GTT, lowercase. GTT is how we abbreviate drop. All right, so choosing a drip set. Macro drip sets, the 10 or the 15 drops per mil, are generally used for fluid administration because they allow for quick administration of large amounts of volume. So say you have a patient that got their leg amputated traumatically. Putting a micro drip set, a 60 drop drip set on them isn't going to give them the fluid volume that they need right now as compared to a 10 drop set. And if you'll remember, the 10 and the 60 and the 15 that were referred to in drop sets is how many drops it takes to equal 1 mil. So in a micro drop set, it's 60 drops to equal 1 mil, whereas in a macro drop set, like a 10 drop, it's only 10 drops. So if we're really wanting to hammer them with a lot of fluid, we'd want to use the macro drop set, a 10 drop set, or a 15 drop set for the tubing. The 60 drop is usually reserved for medication administration, especially when there are small amounts of medication concentrations we want to give. All right, so let's talk about some IV drip formulas. Give yourself a new title for this one because there's going to be some formulas that some people have trouble with, and I don't want it to be confusing for you, so I'm going to get it into a new section. There are two formulas that we can use when calculating drip sets, or drip rates, excuse me. One formula is the general formula for calculating drip rates, and the other is used to calculate specific amounts of fluid administered over time. So your term is general formula, a certain amount of drug with a specified concentration to be given as a desired dose. So our formula would be X equals desired dose times drip set divided by drug concentration. The formula is X equals desired dose times drip set divided by drug concentration. So X equals calculated drip rate expressed in drips per minute, or GTT/MIM, drips per minute. Desired dose is the total amount of a drug needing to be administered, usually defined as a rate. For example, 450 micrograms per minute. That might be our desired dose. A drip set is the number of drips required to produce 1 ml of solution. Example would be a 60 GTT per ml, or 60 drops per ml. Drug concentration is the amount of drug in a vial or bag. For example, 400 milligrams in 250 mLs. That would be written as 400 mg/250 ml, so 450 milligrams in 250 mLs. Our fluid administration formula, it's the administration of a specific volume of solution given over time, and that formula is X equals total volume times drip set divided by total time. So say that we wanted to give 400 mils of volume to a patient, and we were going to use a 10-drop set over an hour. So that would be X equals 400 times 10, convert the hour into minutes, so you got 60 divided by 60. So you would go, the 400 times 10 would equal 4,000, and you would divide that by 60 to get your drops per minute. Total volume is the total amount of volume needing to be administered, like 10 liters of normal saline. Drip set, again, number of drips to produce 1 ml of solution, like a 15-drop set or a 15 GTT per ml. Total time will be the total time of the amount to be administered of the fluid, and say the doctor wants it administered over 8 hours. We rarely will do that unless you're on a specialized transfer team. So you may be asking, how do I calculate drip rates using all this information? So we're gonna put some of that together. Say you're preparing to administer the drug Big Nasty as a drip rate for your patient, and you need to administer 40 micrograms per minute of Big Nasty. If you're using a 60-drop set, you should flow. What should your flow rate be in drops per minute? So let's write it out. You're going to write desired dose, drip set, drug concentration, and calculated drip rate for X. So our desired dose is 40 micrograms per minute. Because we have some time here, we're going to do a 60 drops per ml set, or a 60 GTT per ml, and our drug concentration is 200 micrograms per ml. Now remember, our formula is X equals desired dose times drip set divided by concentration. So let's start plugging some numbers in here. X, which is the calculated drip rate, equals 40 micrograms per minute times 60 drops per mil divided by 200 micrograms per mil. So let's look at that. Where do we get those numbers? The 40 micrograms per minute, if you look back at your notes there that we just took, is the desired dose. So that's the first number you're going to plug in. The 60 drops per mil is our drip set. So we're taking desired dose times drip set, and now we're going to divide it by the drug concentration. Well, the drug concentration comes in 200 micrograms per mil. So let's do some math. So now you got X equals 2,400, because that's 40 times 60, and the micrograms and the mLs will cancel out, over 200. So you got 2,400 over 200 now, and if you do the math, dividing up, it's 12 drops per minute. So let's do another one. You're preparing to administer a drug called Elipoo as a drip for your patient, and you need to administer 2 micrograms per minute of Elipoo. If you're using a 60-drop set, what should your flow rate be in drips per minute? All right, so let's start it off just like we did the last one. Write on your paper, desired dose. Underneath that, write drip set. Underneath that, write drug calculation. And underneath that, write calculated drip rate for X. All right, now remember our formula is X equals desired dose times drip set divided by drug concentration. So let's plug our numbers in from what we know about ELIPU in the original statement. And it says you need to administer 2 micrograms per minute of ELIPU. And you're going to be using a 60-drop drip set. So the desired dose is 2 micrograms per minute. Underneath that, we got our drip set. Drip set is 60 drops per mil. And the concentration of the drug is 1 milligram in 250 mLs, or 1,000 micrograms in 250 mLs. And if you divide that up, so you got 1,000 mcg over 250 ml, divide up, and you're going to get 4 micrograms per mil. So now we know how much concentration is in each microgram per mil. And we're going to calculate the drip rate for X. X, again, is the formula, desired dose times drip rate divided by the concentration of the drug. So let's plug some stuff in. X equals 2 micrograms per minute, which is our desired dose, times 60 drops per mil, which is our drip set, divided by 4 micrograms per minute, which is our concentration of the drug. So you should have X equals 2 mcg per minute times 60 GTT per ml divided by 4 mcg per ml. Now let's do some math and let's cancel some things out. The mcg's and the ml's will cancel out because they're over each other. So you're going to end up with X equals 120 over 4. And we divide up. So 120 divided by 4, and our calculation for X is 30 drops per minute. All right, let's calculate some drug rates for fluid administration. This is really where the advanced EMT has a lot of function. So let's say you've been ordered to give 1 liter of normal saline for your 1-hour transfer, and you're going to use a 15 GTT drop set. So what's your flow rate going to be in drop per minute? So write down total volume, which is the mils to be given. Under that, you're going to write drip set. Under that, you're going to write total time. And under that, write calculated drip rate for X. So let's look at our formula again. X equals total volume times drip set divided by time. So what's our total volume? They say they want us to give 1 liter of normal saline. So a liter is 1,000 mils. And they want us to use a drop set of 15. So our drip set is 15 drops per ml. And how much time did the doctor order? He said 1 hour, and that's going to be expressed in minutes. So if we start plugging in our numbers, X is the calculation of what we want for drip rate, equals 1,000 mLs times 15 drops per liter divided by 60 minutes. Let's do some math. That 1,000 times 15 comes up to 15,000 drops. The mLs cancel out, and we're dividing it by 60 minutes. We're going to divide up. So you got 15,000 over 60. And if you do your math, 60 goes into 15,000, 250 drops per minute. And we would simply set our drop rate using our drip chamber that way. So if you're going to use your Parkland formula, you can calculate that you need to give 10 liters of normal saline to a patient over 8 hours. Parkland formula deals a lot with burn patients, and we will get to that later in your course. So in this patient, you're going to give 10 liters over 8 hours, and you're going to use a 15-drop set, so 15 drops per mil. What should your flow rate be in drops per minute? So we're not going to do anything in liters. We're going to convert it to milliliters. So there's 1,000 mils per liter, and we've got 10 liters to convert. So we have 10,000 mLs, or 10,000 milliliters. So our total volume is 10,000 milliliters. Our drip set is 15. Our total time is 8 hours. Now we're going to convert that into minutes, and we're going to calculate for X. Now let's look at our formula. Again, write the formula down. Every time we give it, write it down. X equals total volume times drip set divided by total time. And so let's fill in the information that we know. All right, let's do some math. So let's start plugging in numbers. X equals, we have 10,000 mils times 15, because that's our 15 drops per mil, divided by 8 hours. Now we convert that into minutes. So we're going to take 8 times 60. We get 480 minutes. Do a little math. X equals 150,000 drops because the mills cancel out, so it's just drops now, GTT. S divided by 480. So you should have 150,000 GTT divided by 480. And if we do some math, X equals 312.5 GTT per minute, or 312.5 drops per minute. You can round that up or you can round that down based on your protocol, but now you have the formulas to make that happen. This stuff takes a lot of time to learn. It takes a lot of time and a lot of practice. So what I've done is I've put together a series of practice problems meant to increase your proficiency and test your understanding of what we've just learned. I'm going to email those out to everybody, complete the calculations, and email the page back to me at barnes.tech@yahoo.com, barnes.tech@yahoo.com. Make sure you have your full name on the email so I'll be able to give you credit for the exercise. The directions are as this. You're going to take and copy the questions to a new page. You're going to work each one out and show your work, and then email it back to me before the next class. As always, I look forward to hearing from you and talking to you again, and see you in the next class. Thanks.